Of course, the most reliable system is often, but not always, but often the one that looks the simplest. And the simplest thing is to actually get rid of the gearbox, get rid of the power converter, and just connect the generator directly to the engine mechanically and directly to the electrical system. The problem now is that the electrical system frequency is going to be variable. Does that matter? Well, if every load has a power converter and the frequency is going to vary between, let's just say, 320 Hertz and about 900 Hertz, my power converter can follow that frequency. A rectifier can easily rectify a frequency in that range. So as long as all my loads are controlled with power converters, then I can have a variable frequency bus on the aircraft. And that's one of the trends for aircraft which have an AC bus, is now to have a variable frequency supply on the aircraft, because my generator system is simple, I don't need a mechanical gearbox, and I don't need a power converter. I've just got a direct connection. So that's the trend at the moment. You could argue that maybe you should go to a DC bus, if you're going to have less copper in the cables on the, or aluminium in the cables on the aircraft. That's a separate argument. I'm not going there in this talk. So, I've got some electrical system on my aircraft. I want to fly my aircraft. It's always a good idea to be able to fly an airplane. So I need some actuation systems. And this picture here is an aircraft that's going to crash very quickly, because you can see all the ailerons are pointing downwards. So this is going to dive down to the ground. Need to redraw that sometime. But these are all the surfaces that I might want to control. Some of these surfaces are critical for flight. The ailerons, control the roll of the aircraft, so whether I'm going to roll to the left or the right. The rudder controls the yaw of the aircraft, so whether I'm going to point to the left or the right. And the elevators control the pitch, whether I'm going to climb or fall. So those are considered to be the primary flight control surfaces. The others, like the reverse thrust, the flaps and slats, and the trim on the tail, they're nice. They make the flight more comfortable, they make it a little bit safer, but they're not critical for flight. So when we look at those, primary flight control surfaces, control roll, pitch and yaw, are flight critical. Flaps, slats, air brakes, reverse thrust doors, they're secondary. Makes it more comfortable, makes it safer, but they're not required. So they're secondary actuation systems. Then when we look at electric actuators that we might use, this is the obvious thing to do. Have a power converter, drives an electric motor, drives some sort of gearbox, which drives a ball screw, a mechanical ball screw. And if you ask somebody for an actuator to move something, and you don't tell them which technology, this is the one they will use. It's great, it works. The only problem is that when you come to certify your aircraft, they say, how do you know that that mechanical system is not going to jam? The way they get redundancy on an aircraft for the actuation systems is to have 3 actuators, say, on each surface. If one actuator fails, they just use one of the other 2 to control it. As a passenger, you would never notice the difference. In fact, the pilot barely notices. Okay? So, if one actuator fails, you still have to be able to move that surface. That's the safety case. If, when an actuator fails, it can jam that surface, you've lost that surface. If that's primary flight control, you lose the aircraft. That's not a good place to be. So, secondary actuation systems, we might use this. Primary, at the moment, they're very nervous, but there are solutions. We'll see in a few minutes. So the other technique they use is what they call ElectroHydrostatic Actuator. We still give a little bit of a job to the hydraulic engineers, and we have a power converter driving an electric motor, driving a small local pump, which drives a small hydraulic ram, all local to the actuator. And the great thing about this is if it fails, I can move that surface with a different actuator. It fails in a benign way. So I can just have a little bypass valve on the actuator, and I can just use this actuator as a damper if I've lost the electrical motor or the power converter or the pump. So, nice, benign, safe failure mode. So for primary flight control with electric actuation, this is the system they use today. And you'll actually find some of these in the tail of, to control the rudder of an Airbus A380. So it obviously works. So the EMA is a direct drive solution. It has a potential for jamming, but it's the most compact solution. The EHA is preferred for the primary flight control because it has these benign failure modes. That's just an example of the way we have to think when we're working on just the more electric aircraft. I want to move on to the all-electric aircraft. How are we going to have electric flight? Well, you could argue we've already done it. I've just put two up here just as some examples. The Solar Impulse was a solar-powered aircraft. It took 60 days to get around the world. Okay? So for those of you who've come from China, this would have taken you a whole month to get to Chile. Okay? Yes, it is great to demonstrate that you can get around the world using solar power, but it's probably not the way we're used to flying today. Okay? We'd like to do that in 1 day or less, not in a month. Okay? But it proves you can do it. And that aircraft is interesting. It's interesting in a lot of ways. One is it's got lots of propellers along the wing of the aircraft. Each has its own electric motor. If 1 or 2 of those fail, who cares? The aircraft will still fly. We'll come back to that one. Another one from a major manufacturer is the Airbus Electric 2-seater aircraft. It's great. It flies. It flies for about 20 minutes on a charge of the batteries. The next generation of this, they've actually put a small engine in the back of it to keep the batteries charged up. Okay? So it's not an electric aircraft, it's a hybrid aircraft. And the reason for that is the same reason that every day when you go back to your hotel room, you plug in your mobile phone. Lithium-ion batteries don't store enough energy yet. So coming back to the battery technology. When your mobile phone is charged once a week, this will be able to fly for a couple of hours, probably long enough for a 2-seater aircraft. And that's one of the problems we have to encounter when we're looking at all-electric aircraft. How are we going to get the electrical energy storage we need when the battery technology we have today is not going to do that? So, the obvious thing to do is what we first did with electrically driven cars, is to have some hybrid solutions. So we can imagine having a parallel hybrid or a series hybrid solution. The difference between those is whether you have a direct mechanical link between the prime mover, in this case a gas turbine, and the prop that is actually moving your aircraft, or whether you do that completely electrically. So in the parallel hybrid, I have a power converter that can put energy into the system or take it out. With a series system, I'm just generating lots of electricity from my gas turbine, and then I'm using that to drive the propeller, maybe with a little bit of local energy storage as well, so that I can optimize the use of the gas turbine. Why might I want to do that? Well, there's different ways in which I can organize this. I can use a smaller engine on the aircraft and use the electrical system for takeoff and climb to boost the output of the engine at times when I need that very high thrust to get the aircraft off the ground and to fly. And then I have a smaller engine on the aircraft for when I'm just flying normally. So that's a nice way of doing hybrid, to get a small increase in the efficiency of the aircraft. The other thing I can do is to put the gas turbine inside the body of the aircraft. So rather than having it out on the wings, messing up all the airflow and creating drag, I can put it in line with the passengers in that metal tube that we all sit in. Okay, just put it at the back of there, and then it's not creating the extra drag that it does when you put it on the wing. So various different ways of looking at how we might organize the aircraft in that case. So, when we're looking at this, what we find is if we're going to do propulsion with electrical machines, the electrical machines and the systems around them, including the power electronics, need to get smaller. They need to get lighter. And we're looking here at some goals for the electrical machines, and I've put in the goals for the cables. I haven't put in the goals for the power electronics because you can always argue about these things for far too long. And over the next 10, 15 years, we're looking at getting to about 20 kilowatts per kilogram for the electrical machine. This includes the cooling system. Let's say I can make the electrical machine smaller as long as I have a large room full of cryogenics, because that doesn't work. It's the system you have to consider. And the same with the cables. So the short to medium term goals we can do with conventional systems. We can do that with the kind of machines we have today, just by being clever with the design and the technology. When we start looking at those long-term goals, getting to 50 kilowatts per kilogram for my electrical machine, for example, we might need to do something a little bit different. Is that going to be superconducting machines and superconducting cables? I'm not sure, because every time I see a lab with superconducting machines in it, I see a very large room next door full of all the cryogenic equipment. You can't do that. You've got to get the losses down in those machines and the size of the cryogenics down to make it a viable system, because it's the system weight that we're after, not just the electrical machine. So, where are we at the moment, and what are these conventional technologies that are going to help us? In the bottom right of this chart, we have a bubble map. For those who don't know the aerospace industry, technology readiness is about the state of technology. So technology readiness level 1, if you've just had an idea over coffee with somebody you were chatting to, and you said, oh, that might be a good idea, very novel idea, not tested, not thought out at all. Technology readiness level 1. Technology readiness level 7 in aerospace is something that's been put on an aircraft and flown. Technology readiness level 9 is a product, okay, that's been well tested in its application. So when you get to working in university research, typically technology readiness level 1 up to 3 or 4. Industry will then develop that from 4 through to 7. Then it goes into product launch and so on. So, when we look at some of the technologies we might use, we see things like superconductivity, very low technology readiness level. But the other axis there is impact. So if they can sort out superconducting machines and superconducting cables, it's going to have a big impact, but at the moment, it's not really ready. We have a look at things like wide bandgap semiconductors. So what we can do is power electronics, and that's that big green blob there. That's going to have lots of impact, but we can do that today. We've seen at this conference people building power converters that are smaller and lighter out of silicon carbide, gallium nitride, and so on. And we heard about those from Alan, particularly yesterday morning. And when we look at things like new magnetic materials, yeah, those are available today. They're already in some products. We can use them very easily. So lots of different things going on there which are going to allow us to make the power electronics smaller, although there's a question on reliability we heard yesterday. It's going to allow us to make the electrical machine smaller and make the whole system lighter and more efficient, hopefully. When we look at some of the performance limits, this is looking at electrical machines, and these are trend lines in terms of sort of the goodness of the machines. So we're really heading for that top pink trend line there. One thing you'll notice is that those dots represent different types of machines. Switch reluctance machines, permanent magnet machines, asynchronous induction machines. And what you'll notice is that they're scattered everywhere. There is not one machine type which always wins. And you see this. We have various different dots that come up on here, and you'll see some of the best machines. I think it's this next one. There you go. This is actually an induction motor. So one of the most power-dense machines I can create is an induction motor if I get away from the traditional building methods and start reinventing how we design that induction motor. So don't think there's one machine type which is always going to be the smallest and lightest for any particular application. That's not quite the case. So, as I said, electric flight, we've got this problem with energy storage. If I put solar panels on there, I have to fly very, very slowly, and that's not compatible with our lifestyles today. So the first systems are likely to be hybrid propulsion systems. And there's a number of different ways of looking at the architectures for this. One is to have some conventional gas turbines driving some conventional props on the aircraft, but to also put some generators on those engines and to use those generators to drive some other motors, to actually oversize the gas turbines, have them directly mechanically coupled to some propellers. A mechanical shaft is generally quite reliable, and we understand very well how a mechanical shaft fails. So we have a system there which is relatively reliable, and we understand the failure mechanisms. I can have some energy storage around those, and then I can have some generators, and they can drive other electric propulsors. I can then start to do clever things with the airflow over my aircraft wings to make the whole aircraft more efficient. So that's one sort of system that you could imagine. People are generally comfortable with that because they can still see a gas turbine connected to a prop, to some fans that are driving the aircraft through the air. The fact there's some other fans there that help it is good, but it feels safe. People quite like that technology step. The slightly bigger step and the harder step to take is to have the gas turbine actually inboard of the aircraft, to have that driving a generator, to have an electrical system that then just drives the propellers on the aircraft wing. Lots of advantages in terms of the efficiency of the aircraft, lots of advantages in terms of the weight that I have to put out on the wing and so on, but we're taking another step in technology, and people might not be quite so comfortable with those steps. But we can do it, and those sorts of technologies that are being demonstrated with the Airbus E-fan and various Boeing aircraft and so on. So just take a quick step back and look at some of the technologies that we're proving and that journey towards those power densities that I need in the electrical machines and the power electronics. We had a look a couple of years ago at an application which is to put a generator embedded in the engine, but to also use that generator to start the engine. But most of the time it's going to be generating electrical energy. So you can see at low speed I'm in motoring mode. That's to start the engine. It's acting as a starter motor. Once the engine gets up to about 20,000 RPM, I go into a generating mode, and the aircraft can be spinning anything between on this particular shaft, anything between 19,000 RPM and 32,000 RPM. And I need to generate across the whole of that range. If you've ever done any motor drive control, you'll recognize this shape. It's going into field weakening, obviously. Okay? So you've got a flat area where you need to produce lots of torque at low speed. Interestingly, at low speed, the efficiency doesn't matter. You don't spend a long time starting your engine. So the only area where I'm interested in efficiency is at the top end there, where the machine is going quite quickly, and when I'm generating onto the electrical system. The efficiency in motoring mode is very, very, doesn't matter. It's irrelevant to the question. And we looked at various different machine types for this, an induction motor, switch reluctance motor, and two permanent magnet machines, one with surface-mounted magnets, one with interior-mounted magnets. We actually went for the surface-mounted one, despite the fact the efficiency wasn't quite so good. The reason for that was our customer was very interested in the manufacturability. Interior magnet, permanent magnet machines, it's harder to manufacture. It's easier to stick the magnets on the outside and put a sleeve around it than it is to start feeding those magnets into the machine. So the reason we chose that machine was all about the manufacturing cost. Obviously, we need some power electronics to drive this, and it's very easy to start talking about efficiency when you're looking at this, but you also need to look at the distribution of the losses and why those losses are occurring. When we built this, we couldn't buy silicon carbide devices at the current levels we needed in packages that we could use in this project. So we looked at silicon rather than silicon carbide, and we compared a 2-level converter with a 3-level converter. So this is a basic 3-level neutral point clamped converter. And as you can see in the chart at the bottom here, the first set of data is for a 3-level converter, and the bottom set of data is for the 2-level converter. So the difference between the inverter and the neutral point clamped. And you can see two things there. One is that in the generating mode, which is the top two of those two sets, the 3-level converter is obviously a little bit more efficient for a particular operating frequency, because the losses tend to be dominated with a lot by the switching loss. More importantly, you can see where the losses are. And you can see that in the 3-level converter, when I'm generating electrical energy onto the supply, the diodes are taking a lot of the loss. It's the conduction loss in the diodes that is dominating that loss mechanism. When I'm starting the engine, it's the IGBT that's taking that big share. When I look at the inverter, the bottom set there, I'm seeing that it's the switching loss that is really dominating the scene. Those big blue bars are a lot longer, and that's causing me the problem. And interestingly, when you start looking at the failure mechanisms in power devices, those are the problems that are going to, that's the loss that's going to cause you the failure mechanisms, those pulses of heat within the device. It's going to start causing the delaminations and so on. So there's reasons there with the reliability why the 3-level converter, despite the fact it has more devices, might actually be more reliable. And for that, we need to start understanding the physics of failure within the devices and really understanding what those mechanisms are. Not statistically, but as Alan was saying yesterday, actually looking at these in terms of material properties and in terms of how the devices are being used. Anyway, we built all this and tested it. You can see the machine there at the top and the power electronics at the bottom. It's housed in a particularly strange shape because it has to fit into a cooling duct within the aircraft. And the interesting thing about this was when we looked at the machine power density, we found we were at 16 kilowatts per kilogram, right in the middle of that 10 to 15 year target for electrical machines. Okay? Well, why is that? Well, that's because we're a university. We should be 5 years ahead of the industry. So we're quite happy with that. And so were the industrial partners involved in that project, because we were showing that we could get to levels of power density in the machine that they didn't think was possible yet. Okay? So we're starting to demonstrate those medium-term goals that we had for the power density of the machines. I mentioned actuation earlier on, and one of the things we've been looking at is swash plate control for a helicopter. And I mention this because it brings in safety. So what we're doing is replacing traditional actuators that control the swash plate angle on the helicopter here. Not for a little helicopter, these are big ones for transporting 20 people, 30 people. Okay, so these are big military or big supply type helicopters. And the problem with this is if that actuator doesn't work, your helicopter makes a controlled emergency landing, i.e. it falls out of the sky. Okay? You get a bit of self-rotation, it does slow it down as it crashes into the ground. So, nice application, very, very, very much in the line of being flight critical. So, could we do this with an electrical system? And the answer is yes. What we were doing is to replace those actuators with a dual electromechanical actuator. And what we wanted to do is some optimization. Now, when you look at papers about optimization, you see lots of papers about optimization tools. I have a problem with that because when you look at the system that you have to put together for the power electronics, the electrical machine, and the control, all these models, when you're doing an optimization, all these models have to be scalable. You have to know that if you change the switching frequency, what effect is that going to have on the input filter, the output filter, the EMC, and the losses? It all interconnects. It takes years to put these models together. I don't care how long the optimization process takes. If it takes 2 days or 2 weeks, who cares when you've spent 2 years putting all these models together? Okay, so the modeling, the optimization technique we used in this one is quite a straightforward one. It's a particle swarm technique. It really doesn't matter, but there's just a simple example there of for the electrical machine, looking at the aspect ratios of the electrical machine and looking at the optimization of that from our first best guess, which was going to give us a motor and inverter weight of about 5.5 kilograms, and it came down to just over 3 when we went through the whole of that optimization process. System optimization like this is not easy. We could do with some better automated tools, if for no other reason than to generate the models we need, those scalable models. It's very difficult to get that right. If that data's wrong, the optimization is automatically wrong. So this is what the system looked like at the end. We ended up with an actuator with 2 motors, 2 EMAs. So if one of them fails, the other one can still move the swash plate surface. We had electrical machines. You can see the size of them there. There's a standard pencil alongside the machine. And each machine has 2 sets of windings. So it's effectively 2 machines in one. So if I lose a winding, it doesn't matter. The machine will still spin. So this type of actuator has to be built so it can survive and operate with 2 failures. Those 2 failures could be identical. So 2 machines both failing, I still need to be able to operate the actuator. That's the safety case about why the helicopter won't fall out of the sky. So the final bit I wanted to have a look at, slightly crazy a bit, maybe not. For a long time now, we've been launching military aircraft off ships. Traditionally done with a steam catapult, more recently done with electromagnetic catapults, or at least we're looking towards that. Not a new idea, it's been done for a very long time. But why can't I do that with my civil aircraft? Well, we can. There's no reason why not. We can design an electromagnetic launch system and have a nice linear machine, and we could catapult an aircraft into the air. Okay? It's been done in a military application. What's the problem? See a few people sniggering. There are some things that you need to think about. One thing is passengers on an aircraft are not trained military pilots. We don't really all want our elderly relatives to suffer 5G accelerations. We couldn't find any data on what you are allowed to subject your 80-year-old granny to in terms of acceleration, except for in fairground rides. So we based it on 0.6 G of acceleration, which is actually a standard for a ride at a fairground. Okay? So we're allowed to do that. And went down to some of the reasons why we might do this. Well, one reason we might do this is to reduce the length of runways. In some countries, and the UK is a great example of this, we don't have very much space for airports. If we want to make Heathrow Airport bigger, we have to demolish 2 towns. Okay? People don't like that. So, but if we start using electromagnetic launching, I can make the runways smaller. I can fit more takeoffs into a particular area of land. So in places in the world where land is expensive, great idea. Fuel consumption. This is all about making air travel more efficient. If I accelerate an aircraft with a land-based system, I'm not having to carry that fuel, I'm not having to carry that energy storage, and my engines will become smaller. So my fuel consumption goes down, my noise and my emissions at the point at the airport will be reduced. So that would work quite well. So we're getting this noise reduction, this fuel use reduction, and a reduction in the size of the engines, which again reduces the drag and the weight of the aircraft, because I'm using a land-based system to catapult the aircraft into the sky. So it begins to make some sense. There is a but. When we compare what we're going to do, so I've compared here an F-35 with an Airbus A320. When you start looking at the mass and the takeoff speed and so on, you're realizing that if you can do it with an F-35, we can do it with a a civil aircraft. The differences aren't that great. You can see there that with an F-35, you can argue about the acceleration figures. The official one is 3.3 g of acceleration, and I'm saying that with an airline, 0.6 g is probably enough. But you're getting the idea of what we're doing isn't too crazy. It could be done if we wanted to do it. When we start looking at the technology, we can start looking at permanent magnet machines for the linear motor. I point out here, linear motors, the concept is about 130, 140 years old. This is not a new idea for a linear machine. The people were making linear motors before they make motors that go round. Okay, it was the first electric machine papers were all about linear machines. We can do it with permanent magnet machines. We can do it with induction machines. We also looked at doing it with superconductivity, but that's not a really particularly sensible idea for an electromagnetic launcher on land, because you don't really care about the weight of the system. It's sitting on the ground. It doesn't matter if it's a little bit big. So we looked at these, and we can compare them. What's the problem? Well, it's a good way of launching an aircraft. The problem is very simple. We have a lot of infrastructure for conventional aircraft. To change every airport that we're going to fly large aircraft to on the planet to ones with electromagnetic launch systems is going to take some time and some political effort and a lot of money. And so it's that implementation problem which will probably stop this happening for all but maybe some special systems. We have, for example, between Paris and Toulouse in France, they have an aircraft flying every 15 or 20 minutes. Well, the idea of having those just being, having an electromagnetic launch system works quite well. You could do that. It would be quite an acceptable thing to do because it's a specialized aircraft that just fly between those two towns. So maybe that's the way of doing things. It's a different way of thinking. It's a different way of getting efficiency into aerospace. So, to conclude, the more electric aircraft, there's still plenty of challenges for us to address, particularly in the condition monitoring, particularly in making the system smaller and understanding the drivers, the reliability, so that we can decide when things are going to fail. All electric aircraft, the technology requirements are demanding. It's not really possible today, but we could be looking at it. And it's certainly the research space that we should be in. And hybrid systems will be followed by true electric if we can get the energy storage or the systems we need around that. And you can look at some out-of-the-box approaches. The advantages are many, but the infrastructure requirements are somewhat daunting. So thank you very much for listening. And before you ask, that is an electric motorbike, but no, it's not me riding it.